So at the center of the space-time manifold, where we would expect the Planck's distance at singularity, we find the vacuum state polarization. This is why the vacuum has polarity and structure, because space-time has angular momentum, is rotating, which generates acts of rotation that generates structure in the space-time manifold. And so we approach the center of the torus, we approach that point towards the Planck's distance, and we used group theoretical models to look into there and solve that point for subatomic particle. And when we were able to solve all the subatomic particles, okay, for that point, all the particles we observed, subatomic particles for that point, which were now linked in our mathematics to the space-time manifold for Einstein field equation for large objects, when we went to that point, the solution gave us a vector equilibrium. Okay? This is a solution given out of a set of mathematics that had nothing to do with my instinctive and logical thoughts that have brought me to believe that this had to be the geometry of the vacuum, the geometry of singularity. Yet the mathematics totally confirmed it. This all came together in a beautiful way that generates a full unified field theory in which the dynamics of space-time is that feedback loop between the gravitational field going in and the electromagnetic field going out, and the center vacuum structure, the singularity, which is the fractal space-time grid that defines that field equation. All put together, you get all the particles of subatomic particles and all the mathematics you need to solve gravitational fields, the electromagnetic field, the strong and weak force. Thank you. So there's still a lot of complexity built in. I think that complexity is going to really reduce when this is fully understood, because I believe we can make way with the strong and weak force. I think those are inventions of humans. They have nothing to do with reality. They have nothing to do with the atom. You see, what happened is they discovered nuclei of the atom, and they found that there was protons in it. Those are highly charged, positively charged particles. If you take two positive magnets and you try to push them together, you're going to get a repelling effect, right? Now, when they calculated how much force you would need to push these particles into a nuclei of an atom, those protons all squashed together, that close together, they calculated the force you need to do that had to be extraordinary. And so they said, that can't be gravity, so we'll just invent a new force. We'll call it the strong force. It's strong. And what are we going to do? We're going to make it be mediated by gluons, because it's gluing everything together. Well, okay, that's one approach to physics, and then you can say, well, you know, it's there because we calculated it, but you didn't really ever experience it. You never even measured it. You just think it's there because you can't imagine how those protons could be together without it. Then they found the quarks, and they said the quarks are inside. You see, inside the protons, so they are squashed even smaller. So then they had to have an even stronger force. But they didn't want to add another force. I mean, that would look goofy, right? So they just said, well, that's the color force, and actually the strong force is just a residual force of the color force that's really strong in the middle. Well, if you make calculations for a black hole atom, and you calculate how much gravity there is at the nuclei level of a black hole that size, you have exactly the force you need to keep the atom together, to keep the nuclei together. You don't need the strong force. You're dealing with gravity in the vicinity of a singularity. You understand? And so now you can make away with that force. And so that starts to change your picture of the weak interaction and all this as well.
I would like to interrupt this presentation to give a little more details for the more technical audience. Here I'm describing the atom as a mini black hole. Many would say the atom doesn't have the mass necessary to be described as a mini black hole. However, in this presentation and in my research, I have come to conclude that the atom is interacting with a very highly structured dynamic vacuum, feeding it its energy potential and its density. And as we've seen in the presentation, the density of that vacuum is extremely large. I believe the vacuum is a highly structured, coherent energy that is feeding the atom and that is producing the dynamics that we see as particles and electron dynamics. In this view, then, the strong force becomes the gravitational force in the vicinity of a mini black hole produced by the vacuum structure. The electron is spinning at near the speed of light as a result of it being in the vicinity of the event horizon of that mini black hole. All this gives us a brand new picture of the physics of creation. Let's continue with our presentation.
What I'm bringing in is that, wait a minute, by modifying Einstein field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation, he should be able to solve all the way down to the subatomic particle. And he actually got really close, I believe, at one time. Because a French mathematician contacted him that was giving him solution to his own equation that incorporated torsion. Torsion is the distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, you know, maybe we could solve Einstein field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque in the first place. And that they never went to. They never added the torque to the space-time manifold. If you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum, and everything, but omitting to add to the analysis the V8 engine that's spinning it. Now, when you look in nature, you can see these dynamics. Look at this. This is a galaxy.